So, we are going to continue with our discussion on energy considerations in internal flow, and what we have seen is that when we do an energy balance, that is whatever be the energy comes in with the fluid and when it goes out it gains some amount of energy. So, it is simply going to be the energy gain is simply going to be mCp delta T. We also understand that something is being added from the side walls by Newton's side walls, the energy that is being added, and it can be expressed in terms of Newton's law of cooling. So, the dQs, if I consider a differential area element, the amount of energy which is being added from the side walls by the convection would simply be whatever be the flux multiplied by PdS, PdX. So, dQ convection, the differential amount of energy which is being convected into the fluid is equal to the flux multiplied by the perimeter times dx, where dx is the elemental length of the fluid element. So, dq convection is q double prime s multiplied by p dx, p being the perimeter, and for a circular pipe the p is simply going to be equal to pi times d, where d is the diameter of the pipe. Now, if q s double prime is a constant, which was the previous case, condition 1, constant surface heat flux, in that case I can simply integrate this, and the total amount of heat which comes into the fluid, which is q convection, can simply be stated as q double prime s, which is the constant surface heat flux multiplied by p times L, where L is the length that we are considering in fully developed flow. And from there we have obtained that how does the mean temperature of the fluid vary with axial position, and we saw that for the constant heat flux condition, this variation in the mean temperature of the fluid is going to be linear in nature. Now, we are going to extend our discussion, include the second condition where the temperature of the wall is kept constant, and we would see how would the average temperature T m of the fluid change with axial position, and can we obtain something which is similar to Newton's law of cooling. What would be the form of temperature difference to be used in that case? That is our goal. So, we are going to start again with the equation that we have derived before, where the variation in the mean temperature is simply going to be perimeter m dot Cp H Ts minus Tm that we have shown before, and we are simply defining a delta T which is Ts minus Tm. So, this in the case, this is going to be the surface temperature which is constant minus Tm, the local value of the mean temperature. So, if I do a differentiation on both sides, so dTm dx is simply, since Ts is a constant, is going to be minus d delta T by dx. In dTm by dx, from this I can write as P m dot Cp H times delta T. So, this is what we can get. Now, you can see I am getting a relation, getting a differential equation in terms of the variation in the temperature difference on the left hand side and the temperature difference on the right side as well. So, I can integrate this equation, integrate the differential equation that we have obtained between the tube outlet and the inlet. So, when I do that, what I would get is the integration d delta T from here by delta T, and initially this is delta T at the inlet and this is delta T at the outlet, and what I have on this side is minus P by m dot Cp and this is going to be h times dx from 0 to L. So, what I haven't done anything additional. I put the delta t over here and took the dx on this side. So, this is going to be my integration. At 0 it is the inlet condition, at L it is the outlet it's simply going to be the outlet condition. Now, when you see this h dx integration 0 to L, I think something should strike you, as I can express this as P L and I put a 1 by L over here. Now, when you consider this part, so I have simply added a L over here and a L over here. Now, when you see this 1 by L 0 to L h dx, what does this tell you? This is the classical definition of length average quantity, and the quantity in question here is h, and therefore, I can write 1 by L integration from 0 to L h dx is nothing but h bar L. So, this is the length average value of heat transfer, convective heat transfer coefficient. This is the definition of length average value. In this case, it is going to be the average expression for the average heat transfer coefficient. So, this entire thing now can then be replaced by h bar L. So, and if I complete the integration, what I get on this side is ln delta T 0 by delta T I to be equals minus P times L by m dot C p into h bar L, and we realize once again that T s is a constant. So, this is the relation one can obtain for the case where the T s is constant, and I have not done anything new except bringing in the definition of the average length average value of the heat transfer coefficient. So, from here I can find out what is del T 0 by del T I, and I am going to write that in the next page. So, what I have then is, from the previous expression, del T 0 by del T I would simply be minus P times L by m dot. I will write it once again. The delta T 0 by delta T I, which by definition is T s minus T m at the outlet, where T s is the constant surface temperature and del T I is the T s minus T m at the inlet. So, this is the temperature difference between the flowing fluid and the tube wall at the outlet and at the inlet. So, this is simply going to be exponential minus P L by m dot C p times h bar. So, that is the relation is going to be. So, the temperature difference, it is not the temperature like the previous case, it is the temperature difference decays exponentially with distance. So, the important observation from here is that, unlike the previous case where for the case of constant heat flux condition, constant surface heat flux, the mean temperature of the fluid varies linearly with x. What we get here is that the temperature difference decays exponentially with x. So, that is the difference when you have a constant surface heat flux and a constant surface condition. So, based on this, I can find out what is the total convective heat transfer that is taking place when a fluid flows through a tube of some length L while the temperature is maintained constant at Ts. So, this Q convection I can write is at m dot Cp Ts minus Tmi minus Ts minus Tmo. Why did I write this? If you look at the expression over here, it would simply give you Tmo minus Tmi. So, Q convection is nothing but m dot Cp Tmo minus Tmi, where this is the mean temperature at the outlet and this is the mean temperature at the inlet. The one that I have here is simply reorganized by incorporating a Ts term over here. So, when you look carefully, this is the temperature difference between the average between the fluid and the surface at location I, and this is the temperature difference between the mean temperature and the surface temperature at O. And also keep in mind that this Ts is a constant in both cases, as the entire analysis is being done for the case of constant surface heat, constant temperature of the surface. So, this I can then write it as mCp delta T, which is this at the inlet minus delta T at the outlet. Now, I write Q convection, I just do a little bit of reorganization, is simply H bar times P L delta T 0 minus delta T I divided by L n delta T 0 by delta T I. Now, where did I get this from? This I am writing it this I am writing the m dot Cp, I am expressing this m dot Cp from the previous relation. So, my m dot Cp is simply going to be minus P L by ln T 0 by T I. So, one can write m dot Cp as minus P L by ln delta T 0 by delta T I times H bar L. So, this expression for m dot Cp is being substituted in the expression over here. So, this m dot Cp, like from the last page, it is substituted as, you can see it here, minus P L by ln del T 0 by del T I times H bar L. So, once you substitute this in here, this is what you are going to get, and look carefully over here. This is area, this is the heat transfer coefficient. What is this? This simply tells you, if I write the expression in this form, Q convection is H bar, which is the average heat transfer coefficient, times P L is nothing but A S, where A S is the surface area, and for a circular tube A S is simply going to be equal to P into L, and I call this as delta T L M. Now, what is this delta T L M? That is, my delta T L M is delta T 0 minus delta T I by ln delta T 0 by delta T I. So, this is nothing but an average temperature difference between the inlet and the outlet, and because of the presence of the logarithmic term in the denominator, this temperature difference with the subscript L m is termed as the logarithmic temperature difference. So, this is another sort of temperature difference where the temperature difference is expressed in the logarithmic form, and for the case of constant constant surface temperature, this logarithmic difference of temperature is to be used if we want to express the equation in the form which is similar to that of Newton's law of cooling. So, Newton's law of cooling generally tells us that Q is equal to H A delta T. What we see in this case is Q is equal to H A delta T L M, the logarithmic mean temperature difference. So, simple temperature difference would not suffice in this case when you are trying to find out what is the total heat that is to be added to the fluid as a result of the elevated temperature of the tube. Then it is simply Q is equal to H times A times delta T, where delta T is Ts minus Tm, but my Tm is a function of x. So, whatever be the Tm at the inlet would be different from the Tm at the outlet, even though my delta T remains a constant. So, this delta T at one location and delta T at the outlet, since they are different, I need to use some sort of an average temperature difference in order to obtain what is the total amount of heat transfer. So, the total amount of heat transfer Q should be equal to H bar, where H bar is the length average heat transfer coefficient, AS, where AS is the total surface area, and we have just now shown that the average temperature difference at the between the tube and the inlet fluid at the inlet and at the outlet is not arithmetic average. We have a different kind of average which is the logarithmic average. So, while expressing the temperature difference to be used with some value of H in order to obtain the total amount of heat transfer, for the case of constant surface temperature, one must use the logarithmic mean temperature. So, this delta TLM, you will see the reference to it, this will come again and again when we try to do the calculation for total heat transfer in internal flow when the temperature of the surface is kept constant, which you would obtain in many of the situations. So, never use arithmetic average of the temperature difference between the inlet and the outlet, always use the logarithmic mean temperature difference between the inlet and outlet, and in conjunction with H and A, they would give you the total amount of heat transferred from the pipe to the fluid. So, this is the new concept which we are introducing here. The relevant temperature difference is logarithmic mean temperature difference for the case of constant surface temperature condition. So, we will expand a little bit on this, and we would see that this is the important relation over here, and this is what is the definition of the log mean temperature, which is also called as LMTD, log mean temperature difference. So, this is log mean temperature difference. So, you can see this is another form of Newton's law. Another form of Newton's law which tells you how the convective heat is connected with the heat transfer coefficient AS and delta TLM. So, we have done these two cases. It is time for us to now apply this concept for the case of laminar flow in circular tubes. So, when we talk about laminar flow in circular tubes, we are looking at the thermal analysis of that. When we are looking at the thermal analysis of laminar flow in circular tube, our starting point should obviously be the equation of energy. Now, if you recollect, the equation of energy contains velocity terms as well. So, the expression is simply going to be u times del t del x plus v times del t del y. These are the convective terms, and on the right hand side I will have terms which are the conductive terms. There will also be heat generation term in there, but we will consider a situation in which there is going to be no heat generation. So, I have on the left hand side I have certain terms which denote conduction, convection, and on the right hand side we will have the conduction part. So, we are going to write simply the energy equation, try to see which are going to be important, and then try to see is it possible to integrate that expression to obtain a definitive, a closed form solution of Newton's closed form solution for the heat transfer coefficient for the case of a circular tube. And of course, if it is laminar flow, we can only do it if it is laminar flow and if it is fully developed flow. So, why laminar flow? Because only in laminar flow I know what is going to be the form of the energy equation. Whenever it is turbulent flow, additional terms due to the formation of eddies which will aid in the transport of energy over and above that of laminar flow would appear, and it is difficult to consider those eddies or the transport due to eddies, the enhanced transport due to eddies in the form of an equation, and even if we do, a closed form solution of that cannot be obtained. So, we would start with the simplest possible case where there is laminar flow, and we will consider only that region from that point onwards when the flow is thermally and hydrodynamically fully developed, and try to see if there is a way to obtain the value of the Nusselt number, the expression for the Nusselt number for the case of constant heat flux and for the case of constant temperature. So, these are the two limiting cases, two ideal cases that we will try to analyze in this part of the class. So, let us start with this thermal analysis. If we write the energy equation is going to be as we have done before, this is the convective part plus V del T del x is equal to alpha, which is the thermal conductivity, by r. I am writing it in cylindrical coordinate system, which is del r of r del T del r. There would be another term over here which would give you sorry, this is del r, which would give you the conduction in the x direction. So, there would be a term for that as well, but if you consider it is a case of a tube where flow is taking place and heat is being added either in the form of a constant heat flux or due to an elevated temperature. So, most of the heat is transported and I have the flow. So, most of the heat is transported in the r direction by conduction, and in the x direction the principal mode of heat transfer is going to be convection. So, conduction in r direction and convection in x direction, these two are going to be the principal mode of heat transfer. Therefore, this part is approximated to be 0. The conduction in the x direction is therefore neglected, only the conduction in the r direction is kept into the energy equation form, which is a direct result of the discussion that I have just made. And since it is fully developed flow, in fully developed flow the V can be approximated to be 0, as well as del u del x would also be equal to 0, And we also understand that the velocity profile of the fluid which is flowing, the nature of this velocity profile is going to be parabolic in nature. So, we are making certain simplifying assumptions in here, that is since it is a fully developed flow. So, there is only the flow becomes only one dimensional, and the moment the flow becomes one dimensional, the other component of velocity is going to be equal to 0, only the u component is going to be present in here, and del u del x is going to be equal to 0, though I cannot say the same thing about del t del x, but definitely the actual velocity will not be a function of position anymore. That is the classical definition of hydrodynamically fully developed flow. And for that flow, we also understand that the velocity profile is simply going to be parabolic in nature. So, this part is already known. I can drop this term, and over here instead of u, I can express it in terms of the parabolic velocity distribution. So, we are going to first solve for the case of constant surface heat flux. What we have done today, we know that for the constant surface heat flux, del T del x is going to be dTm dx. This is what we have done in previous classes for q double prime s to be a constant. So, that's the special case that we would have. So, I put this term over here. So, 1 by r d dr of r dt dr would be 2 times um, where um is the mean velocity by alpha, bringing the alpha to this side, and I am simply substituting u in terms of the velocity profile. So, dTm by dx 1 minus r by r 0 whole square. Just take a minute's time and see if we understand what we have done over here. So, I am writing 1 by r del r of r del t del r. So, this is what I have written over here, only this part. So, this alpha comes over here, and I am going to write u, which is the point velocity for the case of laminar fully developed flow. It is parabolic in nature. So, this is 2 times the mean velocity, which you remember, times 1 minus r by r 0 whole square. And for the case of constant surface heat flux, del T del x is equal to dTm dx, where Tm is the mean temperature of the fluid. So, starting with the energy equation, I have written it for the special case of thermally and hydrodynamically fully developed flow by making the assumption that V is 0. The principal direction of convective heat transfer is here. So, therefore, there is no convective heat transfer or very little heat transfer convection in the r direction. So, this part is taken to be 0. There is no conduction, very little conduction in the x direction. So, the only non-zero components, these two could be the form of the equation, and for u I have expressed twice um 1 minus r by r 0 whole square. For del T del x I am using dTm by dx, since qs is a constant, the rest remains the same. So, this equation, since this equation can now directly be obtained as dTm dx is not a function of r, is the mean velocity, it is not a function of r. So, this equation can be integrated quite easily over here, and what you get after integration is t, which is a function of r, is simply going to be 2 by alpha, which is the alpha dTm dx, and this is r square by 4 minus r to the power 4 by 16 r 0 square plus C1 ln r plus C2. I would advise you to do this integration on your own and see, practice whether you are getting the same result. These C1 and C2 are integration constants. which we need to evaluate by applying certain boundary conditions. So, the first boundary condition that I write is that the t has to be finite at r is 0, t cannot be infinite at r equals 0. So, in order for temperature to be finite at r equals 0, if you look at this expression C1 ln r, so for r equals 0, t to be finite, C1 must be equal to 0. So, my first boundary condition finite t at r equals 0, looking at the nature of the expression simply tells me that C1 has to be 0. And the second one I am going to write, BC2 is going to write t at r 0, that means on the surface is going to be equal to Ts, but we keep in mind that Ts is a function of x. Since it is a constant surface heat flux condition, my Ts is not a constant. So, therefore, when I use these two and I simplify and find out the expression for C2, the final expression would be Tr as Ts. Again, Ts is a function of x, 2 r naught square by alpha dTm by dx, and the inside is going to be, again please do it on your own to practice and to see you are getting the same result. So, this is square. The mean temperature, this T is a function of R. So, if I need to find out what is the mean temperature, which is we are saying as Tm, is given as twice by r 0 square. This we have derived before. Please look at your class notes, u Tr dr. I think the class before the last I have shown you that the mean temperature is this. So, what you have to do is then this T you are going to substitute in here. The parabolic distribution is going to, so this is going to be parabolic, and do the integration. Once you do this integration, what you would get is the mean temperature Tm is going to be equal to Ts, which is a function of x, minus 11 by 48 r 0 square by alpha times dTm by dx. This integration I am not doing this all the steps in here, I am requesting you to do it on your own. And since we know that dTm by dx is equal to q double prime s p times m dot Cp, where p is pi times d and m dot, the mass flow rate, would simply be rho pi d square by 4. So, m dot p expression is known, this Qs is a constant, and I am looking at expression for Tm, which can be used to obtain what is dTm dx. So, when you do that, what you would get is Tm minus Ts. I am looking starting with this equation is equals minus 11 by 48 q s double prime d by k. So, this entire thing, the m dot, this and these three, when you combine, you get the expression, the temperature difference as a function of q s double prime d and k. So, when you use this q s double prime as h times T m minus T s, which is Newton's law of cooling, when you put that in here, the T m minus T s would sorry, this should be q double prime s should be h times T s minus T m. So, when you put that in here, what you get is h to be equal to 48 by 11 k by d, and your Nusselt number based on diameter, which is h d by k, would be 4.36 for q dot x to be a constant. Look at this expression. This is one of the very important relations that can simply be obtained that can simply be obtained by doing an analysis which would give you the Nusselt number to be a constant. So, the uniform QS constant case fully developed both thermally and hydrodynamically, and if it is laminar, if you make all these assumptions, what you would get is Nusselt number is a constant independent of Reynolds number based on diameter, as long as you are within the laminar flow range, independent of Prandtl number and independent of axial location. That is a remarkable result, that when you have such a situation, the Nusselt number turns out to be a constant, and whenever you cite a result, you have to see what are the conditions that you have assumed in order to arrive at the result. So, the conditions that we have assumed is that the surface heat flux is a constant, it is a thermally and hydrodynamically fully developed flow, and the flow is under laminar condition. When all these conditions are met, the Nusselt number has a constant value equal to 4.36, implying that it is not a function of Reynolds number as long as you stay within the laminar flow range. It is not a function of Prandtl number, and it is not a function of axial location. So, a constant heat flux situation gives you an unique value of heat transfer coefficient, and if you know that you are in the laminar flow range, you can simply find out what is the value of heat transfer coefficient for such a situation. Simply equate Nusselt number to be equal to 4.36, and through the definition of Nusselt number find out what is the value of convective heat transfer coefficient based on flow inside the tube. So, what we will do in next class is find out what is going to be the form of Nusselt number relation when instead of a constant surface heat flux condition, I would assume a constant temperature of the inner surface of the tube, and how can I find out this Nusselt number. So, for two very well defined cases, I need to know what is the Nusselt number expression. In one case, I saw Nusselt number to be equals 4.36. We would examine the Nusselt number for the other case, constant surface temperature, in the next class. So, if we do that, at least we have some understanding and we know how to handle laminar flow conditions, and then we have to extrapolate our knowledge of fluid mechanics and our knowledge of analogy to find out what we can do when we have turbulent flow inside a pipe. So, what would be the relation or correlations to be used to obtain Hi for the case of turbulent flow on the inside of the tube. If we do that, then our knowledge is complete. I know how to evaluate Hi for laminar flow, for turbulent flow, and for intermediate flows. I already know how to calculate Ho. Then the overall resistance to heat transfer from the outside fluid to the inside fluid, which is flowing through a pipe, through a tube, will be known to us, which will form an integral part in the design equation of heat exchangers or heat exchange devices. So, we will look at the Nusselt number relation for constant surface temperature in the next class.